So let's wait for a few minutes because I can see people are still joining. Um,
I think Arnie might be wishing to enter.
yeah. So shall we start then?
Yes, I think so.
Um, how about my voice? Can you hear me and can you see my screen and is my voice clear? Can you someone confirm me?
Yes.
Yes, we can hear you, sir. Your voice is clear.
How about the? How about we don't hear anything from here, right?
Okay. Can anyone speak? Emmanuel, for example, or whoever.
Yeah. Okay.
No,
So
we don't. I think now it's should work. Can you just tell Non, Samira n'est pas dans la ligne de la salle.
it's,
Don't.
that's from your screen.
Okay, that's for my screen.
People are still coming, so let's give him. I think it's okay, Franco. It's working now.
Think so. Let's go. Or you want to wait a minute? Or...
Okay. Right. Good morning, everybody. Thank you for joining the workshop. Today we are going to learn how to run OCA 6.01 program, and I will guide you through the basic computations. First, I will give you some background about computational chemistry and what you can do with computational chemistry. And then we can go into the tutorial. And tomorrow we will continue the tutorial, and during my presentation I will not see your messages, but my colleagues can read it, and if you have any questions you can of course post and we can discuss further. If you need some help for the installation, I'm not sure I can help right now, but we will do our best. Okay. All right. First, I want to highlight these two books. That book is Introduction to Computational Chemistry by Frank. Jensen is very useful for learning computational chemistry if you are interested in theoretical background. I don't have much time today to go through all the theory. Please use this as a reference, and this book is available online. You can download for free. And this is Molecular Quantum Mechanics by Atkins. This book is very good to learn basic molecular quantum mechanics. So this is also free, if I remember correctly, and you can download it from internet. Okay, so let's go through some basic ideas about quantum mechanics. In the right hand side you can see a tennis ball, which is a relatively large object compared to atoms and molecules. So roughly speaking, tennis ball is 10 to the power 9 times higher, billion times higher than molecular system. So it is a macroscopic object, but the molecules are microscopic. We can use classical mechanics to describe motion of a tennis ball, for instance. If you throw a tennis ball from one place to another, you can predict the trajectory using Newtonian mechanics precisely. And then you can understand how it behaves. You can see the tennis ball. It is relatively large, which is nice. How about the molecular systems? One of the problem is that it is very small and you cannot really see it. Therefore, we cannot really understand what's going on. It's not like the tennis ball. And molecules can be rather complex, and the arrangements of atoms maybe give additional complexity to visualize it or analyze it if we use a high resolution microscope. Another complicated situation is the dynamic behavior, which is typically in picosecond scale, or if you think about the reactions, it can be in femtosecond scales. So these are very fast processes, and then you cannot really see what's going on because the time scale is very small. To get an idea, I will show you a movie of a simulation, and then you can get some insights about the time. Here in this simulation, these molecules, these are ethylene molecules, ethylene molecules. We mixed and we compressed them together, and then you can see in the colors, the new colors appearing, and it means a new species is formed. And you can see the time over here, which is in picosecond scale, and you can imagine the dynamical behavior of these molecules in picosecond scale. You cannot really see the reactions. I mean, the reactions are happening at femtosecond scale, and you cannot really see it. But if you run this simulation in a computer, you can go frame by frame and then see what's really happening, and you can predict, or you can visualize how bonds are formed, bonds are created, and you can describe the mechanisms of these chemical processes. So it's very nice. So now you have an idea about the time. Okay, now how to understand molecular structures and their properties. One option is to do experiments. For example, let's assume you mixed A and B molecules together and they react to form C. If you do experiments, you can understand A and B because you know what you're mixing, and it's going to give a product here. The product you can characterize using spectroscopy methods. So which is nice. We know what the product is. But the intermediate situations are very difficult to characterize from experiments because the chemical reactions, for instance, are very fast in femtosecond scale, and the intermediates are very difficult to isolate, and the concentration of the intermediates may be very low because their lifetime is very low as well. So it's not very easy to see what's happening in between the starting reactants and the product. So one option is to use computational methods using quantum chemical computations. We use quantum mechanics, and we solve the differential equation. This is a Schrödinger equation, and we can use supercomputers or personal computers to solve the differential complex differential equations, and then you can really figure out what's happening in between here. So it is very nice. For example, if you want to understand this reaction using quantum chemical computations, you can compute the intermediate structures, and of course you can get their energies, and then you know the reaction barriers going from starting point to intermediate to the product, and then you can get overall reaction barriers. You can compute rate constants, and if you have a complicated reaction system, you can analyze the branching ratios. If the reactions are happening at very low temperatures, you can compute quantum tunneling, and you can compute many other properties like binding energies, diffusion barriers, even you can calculate spectroscopy. And pretty much you can calculate anything now. Okay, so it's very nice. Now, when you deal with quantum mechanics, the equation shown here is the Schrödinger equation, and solving Schrödinger equation for larger molecular systems is not practical because of the computational cost. It's not a problem of the theory, it's a problem of the computational cost. In the Schrödinger equation, there are important terms. This is the Hamiltonian operator. It has the all energy terms of the molecular system, and this is a wave function. But because of these practical limitations, in solving the Schrödinger equation for large molecular systems, there have been many approximate methods developed over the past years. And here in this axis, you can see different methods. This end here is the complete solution of the Schrödinger equation shown here. But it is very complicated, as I mentioned before, because the computational cost rapidly goes up with the number of atoms, which is in n, and therefore when the number of atoms in the system is larger, you cannot really apply you cannot really solve the Schrödinger equation using the computers we have. Most popular method nowadays is density functional theory. It describes and it is a very good approximation, and we can solve equations in DFT using relatively simple computers like personal computers if your system is quite small. But even for large molecular systems, we can compute them with with relatively high accuracy, depending on the density functional you choose. And we can obtain reliable molecular structures and also properties we can compute from DFT. And during this tutorial, we will focus mainly on DFT. And we will also try some other methods shown here, Hartree-Fock method, MP2 methods, couple cluster theory. And these methods are computationally difficult if your molecular system is relatively large. And density functional theory, you can see n to the power 3, n is the number of atoms in the molecular system, and density functional theory deals with the density of the molecular system, and the density of a given point can be described by three components, so that's why the n to the power 3 comes in here. So that makes the computational time lower than the other methods. Okay, so now you have an idea about the different computational techniques. I briefly described this, and you can read more and get more information. Now, just to highlight, our interest is quantum mechanics, and our time scale is typically in a few femtoseconds, and our molecular size can be quite small. Okay, it's in angstrom scale, very small molecular system.
Just as a question, the question was why n to the 3 for the computer?
Oh yeah, n to the 3. Yes, thank you. Yeah, okay. N to the 3 because the density of a given point in the space can be described by x, y, and z. So that's why it is n to the power 3. Okay, so it's that's how you can define the density. Right. Okay. If you go into relatively large molecular systems, you cannot really apply quantum mechanics, but different theoretical methods can be applied. If you are in a nanometer scale, you can use molecular dynamics methods, and then if you go into even a larger micrometer, now we are becoming for really bulk systems, and different other theoretical methods can be used. But the quantum mechanics we can apply for really microscopic scale at a molecular level. So just to highlight some milestones over the past 100 years or so. Before quantum mechanics started, the most popular theory was classical mechanics, mainly developed by Isaac Newton. The classical mechanics can describe the behavior of macroscopic systems, as I mentioned earlier. But scientists realized the importance of quantum mechanics in later stage. And 1925, some ideas came from Schrödinger and Dirac. They initiated the quantum mechanics, and they won the Nobel Prize after a couple of years. And some other scientists apply molecular mechanics, which is also a classical description for molecular systems. And it can describe a molecular system with some accuracy. But in molecular mechanics, we completely ignore the electrons, and therefore any property coming from electronic properties will be ignored in molecular mechanics. But still we can use molecular mechanics nowadays to perform molecular dynamics. And semi-empirical methods were also developed it uses experimental data to set up the potential energy the parameters in the potential energy functions. And 1998 Nobel Prize was given to the density functional theory, which has been the most popular theoretical methods when you simulate relatively large molecular systems. Nowadays we use density functional theory in many applications. In 1960s, late 1960s, hybrid methods became available. In the hybrid methods, the idea is very simple, where you combine a quantum mechanical calculation and a molecular mechanics calculation. So you apply quantum mechanics to one part of the molecular system and molecular mechanics for the other part of the molecular system. Then we can calculate relatively large molecular systems with relatively high accuracy. So later 1970s, computational methods were implemented in computers, and people start simulating relatively large molecular systems, not very large, but somewhat large molecular systems. And CPMD, covariant law dynamics, became very useful later. And these methods can simulate, you can run molecular dynamics using density functional theory, for example, for relatively large molecular systems. 1990s, 1990s, the density functional theory has been widely applied for many problems, and different density functionals were developed, and later scientists realized the importance of having dispersion, because the potential definitions in density functional theory has relatively weak dispersion, so we typically add some empirical dispersion effects in the density functional theory. So it's quite standard now. We are now in 2025. I here note down a few very popular and hot topics. Machine learning, artificial intelligence is in the top now. They are making a very fast progress, and people have been applying in many different directions, different fields. Quantum computing is also a very hot topic now, and it is making a progress, and at some stage I hope we will be able to simulate our quantum system in quantum computers. Currently we are using classical computers to run quantum calculations, so that's why our computations are quite slow. So it's going to change very soon. Reaction mechanism discovery is a very hot topic, and we can use automated algorithm now to search very complicated reactions. And molecular dynamic simulations we can do using accelerations in GPUs. So that is also a very nice. So this is an overview about what people have been doing over the past 100 years. Right, so this is very special, right, because we are in 2025, and quantum mechanics initiated almost 100 years ago. So it's a very nice occasion to celebrate. Now, okay, as computational chemists, our primary objective is to compute potential energy surfaces for molecular systems. Potential energy surface is a geometric hypersurface. It describes how the potential energy of the molecular system changes with the coordinates of the molecular system. For example, this is a very simplified three-dimensional potential energy surface, and you can see some minimum or the valleys. Imagine it's like a mountain and it has valleys. These valleys are stable molecular structures or conformations. And if you're working on a reaction, for instance, you are starting a reactant maybe in this valley, and then it can move to a different valley. But when you go from one valley to another valley, there would be a barrier, and the peak point of this barrier is called the transition state. And then you can further move into the even low energy valley here through a small barrier. So if you can compute this point somehow, you can get a lot of information about your molecular system. So this is a primary step in a computational study. This three-dimensional diagram is a bit complicated, and some people like to show these kind of very two-dimensional, very simplified diagrams. But you can even simplify the potential energy surface like this, and this is the energy axis, and this is the R starting point here, and then we have a transition state to go to the second valley over here, and then another transition state to go to the product. So if you can calculate these points, you can compute the energy of a different transition state, or the intermediate reactant or the product, and then we can get the relative energies, which is very useful to get reaction barriers or the reaction thermodynamics. So this is a very simple, very useful in many practical applications. This is a very simple problem. Here I am showing the potential energy surface for the carbon-carbon bond rotation of the ethane molecule. And the ethane molecule has two different conformations, and one conformation here you see the hydrogens are very closer to each other, and in the other conformations the hydrogens are quite a little bit far. So if you come into this conformation, energy of that conformation is relatively lower. But if you are in this conformation, the energy is relatively high. So this is a transition state. This is what you call the local minima or the minima. So when you rotate the carbon-carbon bond of ethane molecule, the energy can change like this. So it will go through some transition states and also the local minimum. And if you want to understand, so this is actually a very simplified diagram, but if you want to get an idea about the three-dimensional potential energy surface, this is a cartoon, okay, just to show you what's the shape in the local minimum. You can see a local minimum, one local minimum here and another local minimum there, and here is the transition state, or we call a first order saddle point. The shape of the saddle point is like this. So this direction you go to the product, this direction you go to the reactant, for instance, and the peak point is energy maximum along the reaction path, but it is a minimum in the perpendicular direction. So okay, so it's a first order saddle point. So the chemist or biologist or physicist, we are interested in first order saddle point, where the reactions go from reactant to the product. So we can compute this point, and then we can get the reaction barriers and so forth. There are many methods to compute the potential energy surface and locate transition states and local minimum. when you start the computation, you have a molecular structure and it has a specific energy, but it is not, it may be not in the minimum energy situation. So our first step is to minimize the energy of the molecular system. So you can use different computer algorithms. I'm not going to go in detail, and if you want to learn more about the energy optimization techniques, please refer the Jensen's book. So the idea is quite simple. You can compute the energy of the molecular system, and then using one of the algorithms, you can push the molecular structure towards the minimum. These algorithms have different approaches. I mean, in some algorithm they only use energy, and using the energy they try to push the molecule towards the minimum here. In some cases they use the gradient of the energy. You can compute the energy and you can get the gradient. Using energy and gradient, you can efficiently push the molecule towards the local minimum. In some cases, they use the Hessian, which is the second derivative. These methods calculate energy gradient and Hessian, and all this information can be used to efficiently push the structure towards the local minimum. So in the tutorial, our first step would be to optimize the molecular structure and find a minimum. And now we can move to the first task, which is geometry optimization. You can start setting up the calculations, and then I will also do the same in parallel, and then you will see how you can do it, and I can also explain some useful information about in the input file, and also some information in output file, and I can also teach you some tricks when you do computations. The input file you can find, let's go to the tutorial. Yeah, here is the tutorial, geometry optimization. This molecular we can create very easily using Avogadro, and here you can see the input file of the OCA computation. So it's a very simple input file, and I will explain the details. So in this input file you can see the first line here, PBE. This is the computational method. You remember is it possible to draw? Yeah, okay. So we use this is Schrödinger equation, right? So the PBE we use to define the Hamiltonian operator. PBE is density functional theory, one of the density functionals, in particular using gradient, generalized gradient approximation. And we define the energy, all energy terms of the molecular system using density of the molecular system. As I told you earlier, nowadays empirical dispersion is very important, and therefore we typically add empirical dispersion, in this case D4. That's going to improve the molecular structure, okay? Def2 SVP is the basis function. Okay, this is called the basis set that define the wave function here. So we want a density functional theory to define Hamilton operator, and then basis set to define the wave function. We are not really solving Schrodinger equation. I'm just just use the Schrodinger equation for illustration purposes. So we are solving Kohn-Sham equations, so which is DFT. Here OPT means you are optimizing the structure. Okay, so and then XYZ indicates that your coordinates are in the Cartesian format in angstrom. And 0 is the charge of the molecular system, and 1 is, this is the multiplicity. In this case, spin multiplicity is 1, which is a closed shell system. I mean, all electrons are paired in this case. And this symbol is important to initiate the coordinates, and then you can we can put that symbol over here to say the program, okay, this is the end of the file. Okay, so this is about the input file. Now you can simply run the computation. So I will try to do it with you. Okay, so I have to cancel this. Right, okay. Depending on the operating system you are using, the procedure may be different. I'm using a Mac system, so I will make a directory in my test1. So you can make the input file here. Now you can see the input file in my folder, and you can run the computation again depending on the operating system. You may be a Windows user, maybe a Linux user, or Mac user. So you can simply execute computation using this command. Okay, so and the calculation is now running, and you can see some intermediate files are formed. So it is running now. Okay, so while you are doing it, I will try to answer your questions. One question is, will the workshop be recorded? Yes, we are recording it and we will upload it. You can watch and study later. Okay, now the computation is finished. So when it is finished, it says OCA terminated normally, which is nice. And now let's go back to the tutorial. When the optimization is finished, it is very important to check the geometry convergence criteria. It has different criteria set to confirm the optimization achieved or not. It's very important to check it. The convergence must be yes in all cases after the optimization. For example, like here. So you can really see it in the output file. If you look at the output file of the computation, let's go through it. I will go to the end of the file. Sorry, this is the wrong file. I want to look at the OUT. Okay. Now, now if you go up, starting from the bottom of the file, if you go up a little bit, you will see some properties. So and you can see the energy final. This is the energy of your final energy of the optimized structure, and also it computes some properties. Sorry. So if you go up slowly, you can see some properties as well. So this is Born orders. So this is called Mayer-Born orders. Mayer-Born orders are very interesting and very useful in some cases. You can get an idea about the presence of single bond. For example, if a Mayer-Born order is 1, roughly 1, it means it has a single bond. If it is 2, it should be a double bond. And I know also you can see some different charges, different type of Millikan charge QA you can get from here. Some orbital information, I will come back to that later. This is another type of charge. Charge can be computed in different methods. So you can see the molecular orbital energies. We can look at the molecular orbitals later. I'm just going up to check the convergence criteria. So here is the convergence criteria. So it says, oh, okay, so all the convergence criteria are met, the optimization has converged. So please make sure that you always converge to the optimized structures. You must see yes for all these different criteria: energy change, RMS gradient, maximum gradients, and so forth. So all must be converged. Now let's look at the optimized structure. Optimized structure you will find as XYZ file, and you can open this using Avogadro software, for instance. Let me open it again. So here you can see the optimized structure. So and of course you can look at the output file using Avogadro software, and if you click here, for instance, animation tool, you can see there are 16 frames in this animation tool. It means optimization went through 16 steps. So this is our starting structure, and then this is what happens during the optimization. You see, the program changed the molecular structure and push it to the local minimum. So, and then it becomes to the local minimum. Another useful file is shown here. This is the trajectory file. Trajectory file has so the 16 structures, and you can see how it moves from the starting structure to the optimized structure. So you can see the changes happening during the optimization. And if you open this trajectory file here, you can see the energy of individual step. This is the starting energy, and this is the final energy. So this energy corresponds to the starting structure, and then this energy corresponds to the second structure, and so forth. But if you plot these energies, you can do it, but I will go to the results, and you will see that actually. So if you get this energy and plot, you can see how optimization went. Here is the energy of the starting point, and then geometry moved towards the local minimum step by step. So then it becomes you know, a local minimum, and at the end of the optimization you can see the energy is converged. Now you can do this very easily. So I will give you a few minutes if you have questions, you can post it to me.
Hello.
Yeah.
Sir, can you let me know that what is the achievement of convergence and why is it required for the optimization or the completion?
Your voice is not clear. Can you type your question in the chat box?
Hello.
Yeah. Okay. Now it's better.
Sir, actually, my query is that what is the actual mean of convergence and why it is required for that calculations?
Other your question is why the convergence is required for the calculation.
Yes, sir.
Okay. So let's go back. Right. Okay. So this is our starting point, and then we move to the local minimum here, and then we want to stop the computation when we reach the local minimum. So how do we decide it? We must tell the program that okay, we really approach to a local minimum, and near the local minimum, if I try to zoom out this part here, okay, so it may be like this, okay. So here is the local minimum. So once you come here, we would tell program, okay, now you have done enough, you should stop. And one option is to look at the energy of that compared to the I mean, let's say this is the previous step of the optimization, this is the previous one, and then you step by step you come to the local minimum. So you can keep recording different properties, and then in the computation we give a threshold to meet. For example, okay, oh no, we can go to the tutorial here. Yeah, okay, so in the energy change, we say when the energy change meets that value, okay, so we are satisfied. We say, okay, now the energy is really converged, and also we can also check the gradients, and we say, okay, we approach to a reliable structure now. And if you don't set this threshold, your calculation will run for very long time. It may not stop. So at some point we should say, okay, we have a reliable structure, and then we should really put thresholds to stop the computation. Okay, I hope I answer your question. There's a question in the chat box. Say we evaluate alanine at a very acidic pK. Can we set the oxygen as anionic? Yes, it is possible. In that case, what you should do, now the charge of your molecule is -1, so you can set here charge as -1, and then it is the anionic form. Do you guys have questions? No? No?
figure out how to launch the first calculation because I'm trying to use Anka.
Okay.
I try to listen to your explanation, but I'm trying to copy paste the text that you
Yeah.
told us to copy paste, and it's not working.
Aha.
So
So shall we have a look
probably
at later?
I have something. Maybe do something wrong.
Okay.
I'm trying techniques
Yeah.
in the meantime.
Another question is the anionic at very high basic, otherwise the okay, there is a question. Okay, I assume that the multiplicity takes into account the whole molecule. That is true. Charge and multiplicity you assign for the whole molecular system. Is there a correct way to calculate the right multiplicity for singlet molecules or molecule? Yeah, it's fairly easy because you know number of electrons in your system. Organic molecules, it is quite simple because if you have even number of electrons, it can be singlet state, all electrons paired. If it is odd number of electrons, you have one unpaired electrons. But in transition metal complexes, sometimes the situation is a bit complicated because it can have relatively high spin states. Sometimes more than one unpaired electrons may be possible. So in transition metal complexes, we typically compute several spin states. If it is a singlet state, we compute singlet and then triplet, quintet, and see which spin state is more stable. So it's a bit complicated situation. But organic molecules typically don't have that issue. So another question, a long question. You showed DFT is less accurate than Hartree-Fock CCS. No, that's not true. DFT, in principle, DFT is more accurate than Hartree-Fock method, and DFT is less accurate compared to CCSD, which is a couple cluster theory. Okay. Does that mean that the exchange correlation factor is more dimensional than level of theory approximation? Do we have some references? Okay. Yeah, there was a misunderstanding here about DFT and Hartree-Fock. DFT sits between Hartree-Fock and CCSDT in terms of accuracy. Okay. Yeah, so I can write answers in Slack, so detailed answers. In the simulation of the ethylene dynamics, how did you set the forces that pulled? Oh, this is a very good question. Yeah, he's asking about my movie. Yeah, this is a very interesting question. Let's go back to the movie and I will explain it. Okay, so he's asking about this movie. So if you run a simple molecular dynamics simulations, molecules move here and there, and they may not meet each other. They can move in different directions. So if you want to study the reactions, conventional molecular dynamic simulation may take very long time. So to avoid that problem, you can artificially add a force there are some algorithms you can find in the literature. You can add a force to the MD simulation, and that force help. So here, shortly, yeah, this is the force adding, okay. And then the molecules come closer, and then it allows molecules to interact each other and make bonds. So if you run a simple molecular dynamics simulation, conventional dynamics, molecules may not come closer each other regularly. So it will take a very long time to get products. So there are some algorithms that you can use to run these kind of simulations. So if you are interested in, I can give you the details. I will,
Professor,
yeah, I will put the details in the Slack, so you can
morning. Also, thank you for the explanation. I was wondering if that was like QMMM or full ab initio.
This simulation is kind of a potential derived from ab initio. It is not really ab initio. I mean, this is not fully quantum mechanical. It's a semi-classical simulation, and there are some techniques. You can do this kind of simulations. I can send the details in Slack, so you can read more.
Thank you.
These techniques are implemented in some software, so you can use.
Thanks.
Yeah. Okay, another question is, can we optimize charge system to or electronically neutral system? You can optimize charged species or the neutral species. It doesn't really matter which species you should use. The only thing matter is the charge and multiplicity. Depending on the charge and multiplicity, you can optimize neutral species, charged species. So it doesn't matter, doesn't really matter. Okay, what is DFT-B? DFT-B is tight binding DFT. So in DFT-B, we assume electrons are tightly bound to the electrons. That approximation help computations to speed up. But at the same time, the accuracy goes down because the electrons are tightly bound to the atoms. And it's going to lose some important quantum mechanical properties like exchange correlations. But it can help you to run molecular dynamics simulation in quantum level, for example. And in OCA, you can use, if you go to the manual, for instance, I have a manual somewhere, not here. Is it here? Oh yeah, it's here. Oh, it's here, okay. Yeah, okay, so in OCA program there are several semi-empirical tight binding methods by Stefan Grimme's group. These methods have been popular very recently, so you can do many different types of computations. These computations are relatively faster than DFT, so you can run molecular dynamic simulations using these methods. It gives reliable molecular structures depend on the parameterization you choose. Of course, you can use this in hybrid computations. You can use DFT to part of your molecular system and XTB methods for another part of the molecular system. There is an exercise in the tutorial we can try tomorrow. Will it give reliable results like GROMACS? GROMACS use GROMACS. In GROMACS, you do molecular dynamic simulations using force field methods, and in principle, XTB, these semi-empirical tight binding methods are in principle more accurate than conventional molecular mechanics methods in GROMACS, but computer time may be higher. In GROMACS, you use force field methods to simulate proteins, for example. So the force field methods can be better in that case because they have a proper parameterization. So that parameterization may not be available in semi-empirical tight binding, but you must really check and do some systematic analysis. In principle, it would give, if you can really simulate the protein using tight binding, it will in principle give reliable results, but molecular mechanics may perform much faster, I think. I haven't done any systematic analysis anyway. How does spin multiplicity affect the behavior of the system during the reaction? It depends on the molecular system. Sometimes the reaction can be started from low spin states, and it can go through different spin states. So maybe I can find an example for you. Let me check whether I can find an example to show you this quickly. For example, if you look at this is just an example. This reaction you can see here. This is a nickel complex, and this complex has 3 spin states, and singlet and the triplet states are very close to each other. So during the reaction, you can see sometimes the singlet triplet can exchange. For example, if you come here, go through the transition state to the intermediate, you can see you start the reaction from singlet, but sometimes it can cross during the reaction. These kind of situations are very common in transition metal complexes, not in organic reactions. So I hope I answered that question. So okay, let's go back to the tutorial because we should move the next step. Okay, now the next step now you can see simple optimization, and you can do it very quickly for this molecular system. And then the next step is to make sure that this is a really a minimum. If it is in the minimum, if you run the frequency calculation, you will find all frequencies. Here you can see positive values and no imaginary values. Okay. Sometimes during the optimization you may stuck in transition states. So sometimes it happens. Therefore, you must really run frequency calculation to make sure that you are in the local minimum. So the input file is here. We have the same computational method, and now we run frequency. So we can do it very easily. The simplest approach, so we have the optimized structure here. Okay, so this is our optimized structure from the optimization. So you can take the coordinates. This is the coordinate, and then I will set up frequency calculation. So I will change my original file to FREQ, and then I insert here the optimized geometry. And that's it. Now we can run the calculation. So it will be finished in a few minutes. While it is finishing, I will tell you a trick. So if you want to make your life easier, it's better to do the frequency optimization and frequency calculation at the same time. Sorry. So what I mean, in our first computation we just perform optimization, but if you put frequency calculation here, if our EQ keyword here, it will first optimize the structure and then run the frequency calculation. So that's easy actually. So I usually do this, and then you don't need to worry about doing optimization first and the frequency second. So you can simply run them together. So you can run them together, okay? Now our frequency job is finished, and then let's look at the outcome. This is our frequency calculation, and oh no. Our frequency calculation is here, so we can look at the outcome. I open the output file using Avogadro software, and then you can see all frequency values here. You can see the frequencies. They all are positive numbers, so that's good. It means your molecule is in a local minimum. So it is important to check all the time. And if you want to check the vibrations, you can select the vibration and start the animation, and you can see what kind of vibration corresponds to the vibration shown here. And if you want to, you can also look at the vibrational spectrum, which is available here. Analysis vibrational modes, analysis plot spectra. No. Stop animation. Where was it? Yeah, okay. So you can see the vibrations, and you can interpret the vibrational spectrum, for instance. For example, you can see here strong peak around 1800, and then you can go there. This is the 1800 peak, and then you can animate it, and then you see that peak over here corresponds to the carbon oxygen carbonyl bond stretching. So you can analyze the vibrational spectrum. So we can do it later, okay? We have an exercise separately for the vibrational analysis. So now in this stage you can optimize the molecular structure, and you can compute the vibrational frequencies and make sure that your structure is a local minimum. Now you are free to create any molecule and run a simple optimization. For example, let's assume you want to create a molecule from scratch and want to run a computation, and then I will show you how to do it. So starting Avogadro software, you can create molecules. Let's say you want to create a water molecule. No, not water molecule. Maybe let's say you want to create maybe water molecule. Oh, sorry. So it's very simple. So this is the template tool here, and this is the drawing tool here, and template tool has different functional groups and different centers you can select with the specific geometry you can select. So you can play around. I have uploaded I put a link to the tutorial for molecule making in Avogadro. Please look at that web. So if you want to make simply a water molecule, and you can do like this. Now let's say you want to set up the OCA calculation, you can do it from here. You can see the input menu here, and it has inputs for many different programs. So here our interest is OCA, and when you click that, you will see a menu like this, and then you can introduce a title. Test, let's say this is water, and you do the optimization, and then here you can define the computational method. Okay, there are limited options here, but of course we can modify the input file at a later stage, so let's don't worry about these options. Basis set, I will make a relatively smaller basis set to speed up the computation. And here is a charge, multiplicity, number of memory you can define, and this is a gas phase optimization. So, and then if you save the input file, so it can create the input file like this. So this input file, then you can of course modify the way you like. So you can drop these keywords, and then I will do the frequency at the same time. I'm using density functional theory. If you can delete these keywords. In that case, it will use the default memory and number of CPUs. So now let's run this calculation. Create a new directory. Now it is running. So it's a very fast calculation. So I optimized the molecular water molecule, and let's look at the outcome. Now you can see I ran the optimization, and I ran the frequency, and then you can see if you click in this animation tool, you can see optimization. Okay, so there were 21 optimization steps. So you see, no, this is not the optimization step. This is a vibrational frequency. It's running. Okay, so my bad. Okay, so you can see all vibrations are positive, so it's a local minimum, and okay, so let me open it again. So if you look at the trajectory file here, you can see optimization has 1, 2, 3, 4, 5, 6. So optimization converged in 6 steps, and if you check the convergence criteria in the output file, so it's always important to check so you can see the optimization was converged, which is nice. And then we can confirm the vibration of frequencies, so all positive, so we approach to a local minimum. So this is the optimized structure of water molecule. So now you can optimize any molecule you would like to calculate, and then you can run the vibrational frequencies to make sure that it is a local minimum. So I will give you a few minutes to come up with questions, and if you want to discuss anything. Okay, I have questions. Can you say which tutorial did you do so far? I am following the geometry optimization. There's a question about zeros. Optimization hydrogens true. I want to look into the manual to answer this question. Probably it is about making only hydrogen atoms to optimize. Okay, I will be back to you. I want to check the manual. In frequency calculation, is there any convergence criteria? No. Answer is no. Right. Okay. This is related to the optimization. You have a question about. Let me read it again. Yeah, optimize hydrogens true. Yeah, optimization of hydrogen atoms. In some cases, it says. In this case, if you use that option, you're talking about this optimization hydrogen true. It's going to optimize the position of hydrogens while keeping the other atoms frozen. Yeah, so this is true. The zero values. There's a question about the frequencies. Yeah. These the zero values corresponds to in the frequency zero. These are translational and rotationals. Three directions for each component. So 6 components are zero. Yeah, this is true. This is about the translational and rotational modes of the molecules. So they are zero. I want to check the Slack. I haven't really checked it. I wonder you have any questions there. Okay, no problem. Now let's let's look at the manual of OCA program. If you look at the manual of OCA program, this is the manual of OCA program. It's very useful to have. If you type OCA 6.0 manual in Google, you can find this. Of course, I can post it in the chat box. Oh. Why I cannot post it? So I will put it in Slack. So I cannot really post in. I don't know why I cannot post it.
It's not. So we put it in also in the chat.
Okay, good. Now let's look at the manual. It's very important. So you can see different information and how to run computations. It has very detailed information about the input structure of your input file and all the definition. It's very important you go through it. And also the typical calculations you can do. You can see here many different options. Now we worked on geometry optimization. We simply use the geometry optimization and there are many other options you can use. Okay. And we also did vibrational frequency calculations. Now you know how to do it. And there are many other type of computations you can do depending on your interest. Now, if you go into the detailed documentation, you can see the methods you can use. I just want to go. And then you can see different types of methods you can use. Even for the geometry optimization, you can see many options. Sometimes you can optimize the structures by freezing some bond angles, bond distances, torsion angles, and you can see many options. I just gave you very basic instructions to run simple optimizations. Right, okay, I want to talk about the choice of the basis set. As I told you before, the basis set define the it's a mathematical way of defining the wave function. There are different types of basis sets, and it's very important to choose a proper basis set for your optimization. And these are very simple basis sets, STO3G, and we typically don't use small basis sets in structure optimization. At least we should use 631G star. Star means you're adding a polarization to the basis set. So that's, at least it should be 631G. But my recommendation nowadays to use triple zeta basis sets like DEF2 SVP. So these basis sets give much better results. If you can use triple zeta basis sets, it's much better. And if you work with transition metals, you may want to use this Zora. They have relativistic approximations or DKH, relativistic basis sets, and depending on your molecular system. So you can see many different type of basis sets. So the other thing is the computational method. Let me find. Choose of the computational model. So this is the model. Model is the method you compute the energy of the molecular system in a way to define the Hamilton operator. So the simplest approach is Hartree-Fock. And of course, we never use Hartree-Fock computations nowadays because the accuracy of that is not that good. It has very bad exchange description. So DFT is the most popular nowadays for structure optimizations. Now, choice of the density functional. It is a very big issue because we don't have a universal density functionals. What we have is different types of density functionals. So what is the best density functional? So I don't know actually which one is the best. In my research, I typically employ REV revised PBE functional in computation. So maybe B97D is also one of my favorite, and also TPSS I typically employ in my computations. This range separated hybrids are also very good. I heavily use Omega B97X in my research. it gave me reliable results for many practical applications. I highly recommend it. It doesn't mean that the other functionals are bad, but it is my choice. So you can find so many density functionals. If you go down the list, you will find more. Yeah, as I told you before, when you employ a density functional, make sure that it has proper dispersion effects. Some density functional have poor dispersion, so in that case, it's very important to add the empirical dispersion in your functional. Otherwise, your molecular geometries may be not reliable. In fact, when you publish your results, referees always complain you don't have strong dispersion in your computations. They will not accept your paper. Semi-empirical methods are less accurate compared to DFT. So it's better to use DFT for geometry optimization, but if you want to do some molecular dynamics on relatively large molecular system, let's say you have 1000 atoms or maybe even more, maybe I would choose GNF XTB method. It is very easy to apply in OCA program. You can do geometry optimization or even molecular dynamic simulations. So solvation effects are also very important when you run computation. We can do a simple exercise tomorrow. There are some other ab initio methods, MP2 method, and these methods are difficult. These are in principle difficult to apply for large molecular systems, but they give their accuracy in terms of energy. So if you can use it, it's good. If your molecular system is relatively small, you can go for MP2 methods, or even you can go for even higher methods. So these are the single reference methods. These methods can be applied for only small molecular systems. But in the tutorial, there are many examples you can, of course, try by yourself. Okay. Now, I talk about different methods. There are some questions. Is this dispersion required for all types of atoms? Yes. The answer is yes. It is better to use standard density functionals with standard empirical dispersion. I'm asking this because mostly use Gaussian 16. Gaussian 16 always have empirical dispersion. You can add empirical dispersion on the density function you use. Another question is, what are the criteria to choose a good density functional? Oh, this is a this is a a good question. Well, it depends on many factors. First of all, when you use a density functional, will you get a proper geometry? Can you get a proper structure, and can you get accurate properties? For example, if you compute a vibrational or a UV spectrum from a density functional, do you get proper results? So better to compare your results with available experimental data. If you have X-ray structure of your molecular structure, you can compute the structure and compare with the X-ray structure, and make sure that your structure is not far away from the X-ray structure. X-ray structure is of course solid state and very low temperature structure. Your computed structure is more like room temperature situation, so the structures are of course different, but make sure that they are not so different. If you have spectroscopic properties, and if you calculate spectroscopic properties, you can always compare your computed data with the experimental spectra and make sure that they are in agreement. Okay, there is a question about imaginary frequency. If you get the imaginary frequency, how to minimize it? So how to avoid? Oh yeah, okay. So in the tutorial you can see geometry optimization tutorial. You can see it discuss. You can see a discussion about it. Yeah, okay. So if you get imaginary frequencies, you can make your optimization criteria tight. That can help you to avoid it, or even you can make it very tight. But if you use these keywords, you just simply use this keyword in your input file. Just take the tight OPT and put it in the input file, and then it will avoid. It will eliminate the negative frequencies, imaginary frequencies, because the convergence criteria is very tight now, so it will go to very more accurate minimum structure. So in the dynamic simulation you showed, okay, in the dynamic simulation you showed, you probably set temperature for the thermostat and the integration, yes. Okay, how is temperature treated in QM and hybrid? Okay, in a geometry optimization, we don't consider the temperature. Well, we are at 0 Kelvin. So this is the static optimization. Temperature is at 0 Kelvin. Okay. But when we run the vibrational frequencies, you can set the temperature. If you look at the vibrational frequency outputs, for example, so if we don't specify the temperature and pressure, OCA assumes the standard temperature and pressure. So you can find it in the input file, the output file. Yeah, so it's frequency calculation performed at 298.15 Kelvin and 1 atm. So these values are default values. You can of course change during the vibrational frequency calculations. So these are simple structure optimization. They are not molecular dynamics. Okay, this is a more specific question. In my work, generally I optimize a molecule, then I calculate excitation energies and matching with the experimental one. Sometimes it matches with the experimental, still requires dispersion keywords. It depends on the density function you apply. Better to have the ground state optimization with proper dispersion, and then you have a reliable starting structure to work with. So you can see one of my former student, Lakshan, is also replying, and I asked him to help me with answering questions. So they will also reply to your questions. If you want to have a more specific discussion about the problems you have, it's better to write it in the Slack. So then we can help you with some guidance. If OGA didn't terminate normally, can we tell depending on certain convergence? Okay, so some optimization may not converge at your first attempt, because the optimization step in when we optimize our first molecule, it converged in 16 steps. Sometimes it may go more than 16, maybe 100 or even more, depending on the starting structure. So if it is not really converged, you can use the optimized current geometry as a starting point to restart the computation. So imagine in your output file here, for example, if the structure is not converged, if the structure is not fully converged, so if okay, let's assume you found your convergence criteria at the end of the calculation is like this. So you can see in this case the structure is not really converged. So in that case, you can restart the computation from the final geometry. So that's how we typically do that. About this QM, okay, about this temperature and thermostat question, in both QM or QMMM structure optimizations, the temperature is 0 Kelvin. So we don't consider the temperature in this case. Okay, no thermostats are there. But if you run molecular dynamics with quantum mechanics or quantum mechanics molecular mechanics, you must apply the thermostats. So it's a different type of computation. Can we use 2 or more different basis sets for different atoms in a molecule? Yeah, that is true. You can apply. You can apply different basis sets and it depends on your interest. For example, let me go back to this this big molecular system. For example, this molecular system here, you can see this has so many atoms. Here you can see the tertiary butyl groups in this molecular system is a bit far away from the nickel center. So then you can simply apply a relatively smaller basis set for the tertiary butyl group and relatively large basis set for the P here, phosphorus atom, that interacts directly with the nickel. And then if you use a small basis set for tertiary butyl, it's going to help you to speed up the computation, and accuracy may not go down a lot, so it's going to speed up the calculations. Typically I apply a better basis set for the atoms interacting with the transition metals, for example. So in that way the metal ligand bond has a good description. So okay. Maybe starting with the lower level of theory and increase the complexity with the, yeah, that's it depends on the situation. You can start with the lower level of theory, relatively small basis set. It depends on the size of the molecular system as well, and if you can systematically increase the size, it may help. That's true. If you alter the temperature and pressure in the optimization, will it change the potential energy values? No. In geometry optimization, we don't apply temperature or pressure, okay? So no temperature treatment, no pressure treatment. We simply minimize the energy of the molecular system. That energy is the potential energy, okay? If yes, then why? Because Schrödinger equation does not, yeah, okay. That is the case. We don't care about the temperature in that case. When it's advanced to use relativistic effects when running, okay. So if we have transition metals, D block or F block, you can apply relativistic effects. We typically apply relativistic effects, but for organic molecules we don't apply relativistic effects in practical applications. Yes, that's right. Lakshan is right. So okay, so I think we should continue the tutorial a little bit. Now you can do computation independently. Okay, someone has technical troubles. In Slack there is a technical trouble. Lakshan, can you deal with it? Lakshan and Charit, I asked two of my former students to help me, so Lakshan and Charit, could you look into it? Right, okay, so let's go back to my presentation. I have some so okay, so vibrational frequencies, now you can simply do it. So without my help, and simply run the frequency calculation. So you can put OPT keyword here. It will optimize the structure first and then run frequency, but I suspect here they have the optimized structure here added in the input. But you can of course put OPT keyword and then make sure that all frequencies you get positive, and then you can make sure that all are positive. Now let's talk about different computational methods. This is an exercise you do. You don't need to do it right now. This is to get an idea about different computational methods. So the correlation energy is a quantum mechanical property, and describing correlation energy is challenging. Now I will go to the results, and in here what we do is basically compute the singlet and triplet energy gap. Is it true? Okay. Yeah. So this is a methylene molecule. It has two spin states. One is the singlet state, which has all electron paired, and other is the triplet states. There are two unpaired electrons in that case. Now the experimental singlet and triplet energy gap is given here in this reference. It is 9.12 kilocalorie per mole. Now in the Hartree-Fock method, the correlation energy, which is a quantum mechanical property, is not really described. The accuracy is very poor, and then that's why the value is very far away from the experimental value. So you can see it is terrible. So this is why we don't use Hartree-Fock in our computations. In DFT, you can see the correlation effects are there, not fully, but it has some correlation effects. And then the accuracy is much better than Hartree-Fock. But if you go to other methods, when you go down this list, the accuracy of methods become better in a way. MP2 methods are in principle more accurate compared to a DFT. This SCS mean spin component scale MP2. In this case, they use special treatment for spin up, spin down electrons. So it gives much better results than conventional MP2. It's better than DFT, right? So if you go down here, this is couple cluster theory. So you kind of approach to the chemical accuracy. See? And but when you go down this list, computations are quite expansive. Here you have a density functional. This density functional has some contribution for MP2 energy. That's why it has really accurate energy. But going down to this couple cluster level theory is relatively difficult for large molecular system. You can do that. Maybe you will not be able to optimize the structure if the system is large, but you can optimize the structure using DFT and then run energy calculations using advanced level of theory. So please do this exercise, and then you can get an idea about the different methods and the accuracy of different methods. So our objective here is to find exact solution, which is the solution for the Schrödinger equation. We cannot do it practically for this molecular system we deal with day-to-day life. Hartree-Fock methods with a small basis set give very bad correlation effects, so it's not reliable at all. And if you can use relatively accurate methods like configuration interaction methods, you can approach to the exact results. here you can see we are using couple cluster theory, so we are kind of here, somewhere here. But we use kind of extrapolative approach to get to better energy. But so it's pretty good actually. Accuracy is pretty good. So you can approach the chemical accuracy. Okay. So this is a nice exercise where you can learn about the accuracy of different methods. So you can do this by yourself. You don't need my help. If we go into the input files, maybe we can discuss a little bit about the input files. Let's find the tutorial. It's not here, it's not there. Okay. Oh, the correlation energy tutorial is in the old. You should go to the workshop homepage, and then there is the link, the correlation energy. It is OCA 5.0 tutorial, but anyway, it doesn't matter. So here we see, you see, you optimize the structure using MP2 method, and these are the basis sets, and this is the optimization of the singlet state, and this is you can when you change the multiplicity to 3 here, you can simply optimize the triplet state. Okay, you can start singlet and triplet calculations at the same time. Just change the multiplicity, and then you don't need that essentially. Okay, you can forget about this, and then you can get the optimized structures, and then here you place the optimized structure and get the energy, potential energy. So what we do is we use relatively relatively cheaper computational method to optimize the structure and get a reliable structure, and then apply, and then simply calculate the energy of the optimized structure, but we increase the computational method. So that's the common practice we do in our day-to-day life. We do that because it is very difficult to optimize structures with relatively accurate computational methods. It's cost a lot. Okay, so then what we do, we use a relatively cheap method but a reliable method to get geometry optimization, and then take the optimized structure to calculate the energy. Okay, so that's what they did here. So we have about 20 minutes, and if you have questions, I think we can okay, there is a question about changing the temperature and pressure affect the thermodynamic properties calculated from vibrational analysis. Yeah, that is true. That's the answer from Charit. That is true. If alter the temperature and pressure in optimization, will it change the potential energy value? No. Potential energy doesn't temperature doesn't affect the potential energy. If yes, then why? And Charit, my former student, says changing the temperature and pressure affect the thermodynamic properties. Yes, he is right. And not the potential energy of the Schrödinger equation. Yes. Thank you, Charit. Can I get a certificate for attending your workshop? Oh, Well, it's if they want, right? Yeah, if you want, we can give you. But I want to make sure that you attend all sessions. So. Yeah, I want to keep track on you. So. If you have a hello email, you need to. Oh yeah, okay. Yeah, thank you, Carl, for your links to the paper. So it's very useful. So yeah, it has a nice description about. Yeah, it looks nice. It's from Stefan Grimme, so it's a nice paper. So you guys have questions? All good? So now you can independently run calculations. I want to tell you one thing. Tomorrow we will run transition state calculations. These calculations take a little time, so I recommend you to do it tonight. Okay. So if you can run it tonight, depending on the speed of your computer, so it may take long time. So I recommend you to do it before coming to the tutorial. And the transition state calculations, and we can also calculate the kinetic isotope effects, and these are very simple computations. And of course we can go through the steps, and it's better if you do the transition state computation before come to the workshop. I suspect the calculation is a little bit longer depending on the speed of your computer. So you can do, and then you can come up with some questions if you have. And for the multi-scale methods, again, it is a little bit expensive computation, but I can help you to understand the background theory a little bit, and also I can also give you some practical guidelines. This hybrid computation needs a plugin to the XTB methods. It is very simple. You just download the XTB code and then put in the OCA directory, and then OCA automatically knows this XTB plugin is there. So, and then you can simply start running QM hybrid calculations. So this approach is very good when you deal with relatively large molecular systems. So I can of course show you some examples, and we can further discuss about it. So if you have any questions, technical problems, it's time to Is it recommended to optimize a structure in a stepwise manner for CCSD? I think optimization with coupled cluster theory is not really practical. It depends on the size of your molecular system. In what is usually the best practice in deciding the interface between QNMMM and the banding method? This is a good question. I haven't really checked the molecular mechanics methods in ORCA. I will check it today. And when you say about embedding method, it's I will explain. I will give you some slides tomorrow about these hybrid methods. I can find the information in the manual. Okay. Now. I know ORCA uses XTB method, which is not a molecular mechanics methods, and I will check. Probably ORCA has a plugin to ChemShell program. I want to double check. I will be back to you tomorrow. But if we use other programs like Gaussian 16, they have several force field methods, and also I have developed some codes and which are also available. I can highlight those tomorrow, and you can use a wide variety of force fields in hybrid calculations. I can highlight those tomorrow. In principle, the coupled cluster theory gives reliable energies. As I told you before, optimization may be not possible with coupled cluster theory for large molecular systems, so better to have reliable DFT methods to optimize the structure if you have a large molecular system. And then you get a reliable geometry, and then you can use that geometry to calculate accurate energy using coupled cluster theory, for example. It's really hard to optimize large structures with even 15, 20 atoms using coupled cluster theory. So I will be back to you. What is usually practice deciding interface between QM and MM? So we can discuss it tomorrow. I will bring some slides. Anything in Slack? I cannot see it. Yeah. So we have 10 minutes. If there is no questions, we can terminate the session. And so I will leave the Zoom open, and then if anybody wants to post questions, you are welcome. The Slack you can always post, and we will keep the discussion there for a while. So okay, thank you for participating, and look forward to seeing you tomorrow. And please run the transition state computations before come. Okay, bye bye guys, thank you. And I will keep the Zoom available. Okay, if you have questions, you can post it.